Uh, in this exercise, we're dealing with functions which are defined on the real line, but they do involve rationals and irrational numbers. In fact, this was a very hot area of mathematics during the end of 1800 years to the beginning of 1900, and mathematicians were building functions that involves the decimal expansion, weird functions, etc., etc. So this is just an example of what's known as the Dirichlet functions, f of x and g of x. So let's start with f of x first. So we want to show that this function f of x does not have uh, a limit. So assume, so no, number one, so assume that limit of f of x when x goes to a is equal to L, where a is a number belongs to R. So in this case, we want to show, in fact, that we want to generate a contradiction and show that this is not correct. Okay? So what does that mean, the definition of limit equal to L? It means that for any epsilon, there exists delta such that for every x in R, absolute value of x minus a less than delta implies that f of x minus L less than epsilon. Okay? So take epsilon less than 1/2. Okay? And for the delta that we have, okay, for this delta, for this epsilon, consider now the interval x, I'm sorry, not x, a minus delta and a plus delta. So this one we know has a rational number R and an irrational number I. And the reason is because the rationals are dense as well as the irrationals. Okay, in any in open interval, a and b, a less than b, then we have a rational and an irrational number. So what do we have now? We must have absolute value of f of r minus L less than epsilon, as well as f of I minus L less than epsilon. Okay? So clearly f of r is equal to 1 by definition, and f of I is equal to 0, which implies that uh, 1 minus L less than epsilon and 0 minus L less than epsilon. Okay? The triangle inequality implies that 1 minus L plus L minus 0, which is less than epsilon plus epsilon, or 1 is less than 2 epsilon, which implies that 1/2 is less than epsilon, and this is our contradiction because we choose epsilon less than 1/2. Okay? Therefore, such limit does not exist, and therefore f does not have limit anywhere on the real line. So the second one is the function g. The function g is a little bit trickier. And just to give you an idea, a quick idea. So if you take a bunch of, if you assume that you have a limit of g of x, then if you take uh, uh, a bunch of rationals which converge to a, so if you fix a, for example, so fix a in 0, 1, okay, and you are looking at, you want to prove that limit of f of x when x goes to a is equal to 0. So, what's the idea? The idea is that if you take a bunch of x which are rationals which converge to a, okay, then the rationals will be of the form p over q, okay? And what's interesting is that if a is an irrational, this pn and qn, okay, that converges to a, the qn will go to infinity. Okay, so you will have that 1 over qn which converge what? To 0. Okay, and of course if you're taking irrationals, then the image of this irrational is equal to 0, then the limit also will be equal to 0. So the idea here is that the limit being equal to 0 is somehow understandable if you look at, for example, how rationals approaches numbers, especially approaches irrationals. In any case, so let us prove this. And the way to do it, okay, you fix epsilon, okay, and you consider the set A epsilon, so it's the set of irreducible P over Q rationals, which belongs to Q intersects 0, 1, such that 1 over Q is greater than epsilon. So we are talking about uh, rationals in a reduced form such that the 1 over q is bigger than epsilon. Now remember, we want to show that the limit is equal to 0, and therefore we need that f of q minus 0, the limit less than epsilon. That's why you get 1 over q less than epsilon, because if you are taking x, which is irrational, therefore x is equal to 0. In any case, so let us look at this set. First of all, what happened to P over Q between 0 and 1? So this tells us that P is between Q and 0. Good. Next, what does that mean? 1 over Q is greater than epsilon. This tells us that Q is less or equal than epsilon. So basically, what you are looking for are are set of integers p and q, okay, in n cross n, okay, coprime. In other words, we want them to be in a reduced form, coprime, such that p is less than q, less or equal than epsilon, and greater than 0. Okay, so this set is finite. You only have finitely many numbers that satisfy, natural numbers that satisfy these conditions, which implies, okay, which implies that a epsilon is finite. Okay, great. So now let us set delta to be the minimum of absolute value p over q minus a, okay, and this is for p over q, which belongs to a epsilon, and we want p over q to be different from a. Okay, so a epsilon is finite, therefore this delta is positive. So let now x belongs to 0, 1, okay, such that x minus a is less than delta. Okay, and let us prove that f of x minus 0 is less than epsilon. And this will, of course, finishes the proof that the limit is equal to 0 of f of x when x goes to a. So first of all, we have two cases. Number one, x is irrational. That's the easy case. Then, okay, f of x is equal to 0 by definition. Not f, I'm sorry, it's g. So in this case, g of x will be what? Equal to 0, which implies, obviously, what we want, meaning that 0 minus 0 will be less than epsilon. 2. So x is rational, and x is equal to p over q in reduced form. In other words, p and q are coprime. So in this case, what happened is, since p over q minus a is less than delta, okay, then p over q is not in a epsilon. So keep in mind that we can assume that p over q is not equal to a, because in the limit we don't take x equal to a. We can take x different from a. Okay? So in any case, so in this case, what happened? So 1 over q would be less than epsilon, which implies that f of x minus 0 equal 1 over q minus 0 is less than epsilon. So in both cases, for x apart in 0, 1, such that 0 less than x minus a less than delta, we have f of x minus 0 less than epsilon, and this exactly implies that limits, I'm still stuck with f. I don't understand why, and in fact should be g. The function is g. Okay? So what's interesting about this function g is that since the limit, so limit of g of x as claimed when x goes to a is equal to 0, and in this case we have two scenarios. If a is irrational, then limit of g of x when x goes to a is equal to 0 equal to g of a, which means that g is continuous at a. But if a is rational, then g of a is different from 0, and therefore the function g is discontinuous at a. So this function is continuous on all irrationals, but not on the rationals. This is totally different from the function f, the first one, because the function f did not have limits everywhere, and therefore is discontinuous everywhere.